Welcome to this explainer. Today, we're diving into something truly terrifying. When we think of volcanoes, we usually picture glowing, flowing lava, or massive towering ash clouds, right? Well, today, we're looking at what geologists widely consider the absolute worst-case scenario of any eruption: volcanic debris avalanches. This is a geological event so massive and so violently destructive, it can literally reshape the face of the Earth in a matter of minutes. To really wrap your head around the scale of what we're talking about, picture this. Imagine an entire mountainside, literally millions of tons of solid rock, suddenly collapsing and barreling straight towards you. And we are not talking about the speed of a normal landslide here. Because of the incredible sheer drop and the sheer volume of rock, this wall of Earth can reach mind-boggling speeds of up to 250 kilometers per hour. There is simply no outrunning it. So, let's unpack this. Because despite their world-altering destructive power, these massive avalanches remain surprisingly unknown to most people. Our sources note that because they just don't happen as frequently as other volcanic events, they kind of fly under the public's radar. But make no mistake, when the flank of a volcano gives way, it creates a hazard that is completely unparalleled in its lethality.
Here is what we're going to cover today. 1. The worst-case scenario. 2. Anatomy of a collapse. 3. Fingerprints of an avalanche. 4. A ripple of devastation. And 5. Surviving the unstoppable.
The worst-case scenario.
Listen, volcanic avalanches are not your garden-variety landslide. The numbers involved are absolutely staggering. Because of the immense kinetic energy at play, a volcanic debris avalanche travels incredibly fast and unbelievably far. Get this, for every 100 meters it drops vertically, it can blast forward up to 1,000 meters horizontally. Compare that to a non-volcanic landslide, which typically only manages about 166 meters of forward momentum for that exact same drop. That sheer mobility means it can wipe out areas way, way beyond the immediate base of the mountain.
And that crazy mobility, it's driven by unbelievable volumes of material. Just to give you some context on the amount of rock moving around during these events, a single cubic kilometer of debris is equal to the volume of 400,000 Olympic-sized swimming pools. Now factor in that volcanic landslides can range from less than 1 cubic kilometer to more than 100 cubic kilometers. It's honestly hard to even fathom that much earth moving at once.
Section 2. Anatomy of a collapse.
You might think of mountains as entirely solid, unyielding rock, but volcanoes have massive internal weaknesses. Over the centuries, incredibly hot, acidic volcanic gases rise up from the magma and mix with groundwater. This creates a boiling hydrothermal system that literally rots the hard rock from the inside out, turning it into a slippery, weak clay. Now add the intense stress of new magma pushing up into the volcano, making the mountain swell and fracture. You're basically building a steep, massively heavy tower on a foundation of wet clay.
So when that weakened slope finally fails, which could be triggered by something as minor as a magnitude 5 earthquake or even just really intense rainfall, the results are catastrophic. As the side of the mountain slides away, it acts exactly like popping the cork on a violently shaken bottle of champagne. It instantly depressurizes the shallow, boiling magma and hydrothermal systems trapped inside, triggering a massive, highly destructive lateral blast. The mountain doesn't just fall down, it literally shoots outward.
Section 3. Fingerprints of an avalanche. So, how did geologists actually play detective and figure out that these colossal events happened centuries ago? Well, they look for two undeniable geological fingerprints. First, they search for massive, prominent gaps in the volcano's cone called amphitheaters, which are these huge horseshoe-shaped craters where half the mountain literally used to be. Second, they look way down in the valleys for sprawling fields of chaotic, bumpy deposits known as hummocks.
And what's really wild is how bizarre these hummock deposits are up close. We aren't just talking about a pile of loose gravel here. These avalanches carry intact chunks of the original mountain, some as high as 200 meters tall, surfing for miles and miles. These massive blocks remain relatively intact during their high-speed journey, but get heavily fractured, looking exactly like giant, cracked jigsaw puzzles. From the air, these scattered hills of debris create a strange, bumpy landscape that scientists often say looks like giant chocolate hills.
Section 4. A ripple of devastation. But here's the thing. The initial mountain collapse is often just the opening act of the destruction. Because these avalanches move so fast and carry so much mass, if they hit the ocean, they violently displace massive amounts of water, generating catastrophic mega-tsunamis. This isn't just a theory either. This is exactly how over 15,000 people tragically lost their lives during the 1792 Mount Miyayuma collapse in Japan. Historical collapses at Kamagatake, Oshima, and Augustine all generated deadly tsunamis that totally devastated distant coastlines.
And even if the avalanche happens completely inland and never touches the ocean, it still generates terrible secondary hazards. The sheer volume of debris can easily choke off river valleys, blocking streams to form temporary, highly unstable lakes. When these natural dams eventually burst, they send deadly walls of water and thick, cement-like mud flows, known as lahars, miles downstream, wiping out everything in their path. Add in the risk of those magma-driven directed blasts we talked about earlier, and the hazard zone becomes absolutely massive.
Section 5. Surviving the Unstoppable.
This brings us to the most crucial part of this explainer. How do communities protect themselves from an unstoppable geological force? The harsh reality is, they really can't. Because of the extreme mass and speeds involved, with debris sometimes covering areas as vast as 1,500 square kilometers, human engineering is completely powerless. Standard protective measures like those concrete retaining walls used for regular landslides are completely useless against a volcanic debris avalanche. The mountain will simply erase them. So the takeaway is summarized perfectly by this quote right from our source material: even if debris avalanches can be predicted, evacuation is the only option available. That's it. When the warning signs appear, things like sudden bulges on the side of the volcano, unexplainable new cracks, tilting trees, or sudden changes in stream levels, immediate evacuation is your one and only lifeline.
Let's break down the hazard protocols and see how communities actually build a culture of survival, starting with the before phase. You absolutely cannot wait for the mountain to bulge. Communities must have hazard maps drawn up based on past avalanches to identify the danger zones. Your family needs to have an evacuation plan locked in, survival kits packed, and alternate routes practiced long before the mountain even begins to rumble. When a crisis hits, the during phase kicks in, and an orderly, calm evacuation to designated centers is critical. Once you're out of the immediate avalanche path and inside a shelter, you have to stay indoors. Venturing out exposes you to falling ash and a bunch of other hazards. Keep all your doors and windows tightly sealed and have a gas mask or a wet towel ready to protect your lungs from breathing in that sharp, glass-like volcanic ash.
Finally, the after phase requires some intense patience. After the initial collapse, you must never return home until you are officially cleared by the authorities. Why? Because the danger is far from over. Those secondary hazards we discussed, like heavy rainfall, turning all that fresh ash into massive sweeping lahars, can happen days or even weeks later, and they can be just as deadly as the avalanche itself.
As we wrap up this explainer, I want you to consider the lasting, permanent impact of these events. If a debris avalanche totally alters the landscape, carving deep craters and filling entire valleys with hummocks, how might that new local topography dictate the terrifying path of the next collapse? It's like a giant puzzle. Geologists literally spend their lives studying the shape of the land to predict exactly where the next 250-kilometer-per-hour wall of rock will flow.
Which leads me to this final thought for you. If you live anywhere in the shadow of a stratovolcano, how well do you actually know your local topographic hazard map? Do you know the exact path the debris would take? And are you truly, honestly, prepared to evacuate when the mountain begins to move? The terrain tells a story of the past, for sure, but it is also a map of the future. Learn it, stay alert, and stay safe.